and I'm going to title this as Dynamic Programming and Greedy. Okay, and you'll see why. Okay, so we will start with an illustration of another illustration of a dynamic programming problem. Let me start with the following scheduling problem. So the input is a set of tasks you want to schedule in a classroom or computer or in a marriage hall or something like that. So there is tasks. Let's call them 1, 2, 3 up to n. They have a start time and an end time. Each job has a start time and end time. So maybe this will start at 8 and finish at 9. Maybe this will start at 6 and finish at 10. This is a job which starts at 7 and finishes at 12. Here is a job which starts, you can, let's say 14. So it's in the 24-hour clock cycle I'm mentioning, and it ends at 15. And here is something which actually starts at 10 and ends at 16 and so on. Okay, some meeting, some event, some marriage in a hall, and you are given this n jobs, which is start time and finish time. And what is the goal? Right, this is my input, and what's my goal? Find a maximum set of jobs that can be scheduled or non-overlapping intervals. If you think of each job as an interval, okay, so this means that think of it as it's closed interval 10, open interval 16, meaning it just will end a few seconds before 16. So if there is a job which starts at 16, it can be scheduled. Okay. So the start end times or starting time is on the dot, ending time ends just a few seconds before or a few minutes before. Okay, so this is the problem. I want to find the maximum set of non-overlapping intervals. Okay, so let's say if this is the set of intervals, I could schedule example for this above set of start and end times. I could schedule job number 1, that rules out 2, that rules out 3, and then I can schedule 4, for example. Okay, so if these are the 6 jobs I have. Here is one example. Another example, I could schedule 2 and 6. I could schedule 2 and 5 maybe, or 1 and 5. So this is the kind of optimum. So I could, given this 6 jobs with this start and end times, I can schedule 2 of them in my room. Can I schedule 3? I don't know. Probably not. So the goal is to find the maximum number of jobs you can schedule given the start and end times. Okay, and we're going to assume, without loss of generality, assume that my input is given in increasing order or non-decreasing order of the finish times. Without lesson, I mean, you have to give it some order. So let's say I take the jobs and arrange them in non-decreasing order of the finish times. So that's the goal, right? You're given some start and end times, a bunch of tasks. What is the maximum you can schedule? So let's start with an idea. How do I go about doing finding this number using dynamic programming? So if I want to use DP, then we know, let me make a choice, right? Say some job Sk, or K, which has a start and end time of Sk and Tk, is in the solution. So another way to think about this input is that somehow in real line you are given these kind of intervals, okay, start time and end time, and I want to find the maximum number of non-overlapping intervals. Okay. So you are told that some job K is in the solution. What if it's not? We'll see it. If it's in the solution, can I do a recursive formulation, right, for the remaining problem I need to solve? That's what dynamic programming is about. So clearly any job that overlaps with Sk Tk cannot be in the optimum solution the moment Sk and Tk are, job K is there, right? So I have this, let's call S1K or jobs that finish before Sk, and let's say Skn are the jobs that start after Tk. When I say here after, it's greater than or equal to, remember, because the right side is an open interval. So Tk time slot is actually free. Whereas here before means strictly less than. So in my jobs, set of jobs, I find all jobs that finish before Sk and that jobs that start after Tk. Then anything else in the solution must be from this set or this set, right? Maybe both. You are trying to find an optimum solution. Suppose I have said job K is there, then any other job should either finish before Sk or start after Sk. So now the optimum substructure property tells you that you have to find the optimum in this set of jobs, right? So optimum substructure property will tell you that now you find the optimum set of jobs in 1 to K, the smaller interval, and then optimum set of jobs in K to N, and add your K, which is plus 1, and then that's the total number you can add, right? So I can say opt the number of jobs in 1 to N is 1, you've scheduled K, plus opt in 1 to K plus opt in K to N. Okay, so you have an informal understanding of what opt 1 K means, that jobs that finish before Sk, in that look at this and this, right? Now the next question is, what is K? K is a job which I assume it's there. Okay, well, try all possibilities for K. So you want to find max over K. Right, K is between 1 and N. This is a typical dynamic programming formulation. We made a choice of k or job which is there. That means then we got a recursive formulation of all jobs, optimum number of jobs you can schedule in S1k, optimum number of jobs you can schedule in Sk. N plus 1 is the number of jobs maximum you can schedule if kth job is in the solution. But what if it's not? Well, one of them must be in the solution because it's, assuming 1 to n is a non-empty set, there's some job you can schedule. So pick all values from 1 to n and then you can do this. Okay, so that's what the optimum is. Now you're done. Basically, now it tells you what are the sub problems we need to compute. Well, as usual, you think it is 1 to k and k to n for all values of k, but it's not enough. So basically, the sub problems would be opt ij, all jobs that finish after Si, and so jobs that finish, that start after Fi and end before Sj, before j starts. Okay, so this is Sij. So in that you try to find optimum, and then you can. So when I say after, remember it's greater than or equal to, and before means it's strictly before. Okay. So you have the sub problems, compute in this range what is the maximum you can do, and how do you compute them? Well, you pick a guess in between, and then you have a couple of sub problems, and then 1 plus the opt of this, opt of this. So again you can compute bottom up, and so starting with intervals of length 1, you just have to schedule that particular job which is available, no problem with overlaps. Opt I is something it's just 1, and then you can eventually find the optimum number. So the number of sub problems will be I to j. There are some n square segments, and each one requires you some n times. So overall, because this is max I to j, so j minus I. So I'm going to just say n cube time. Okay, so yet another example of a problem that is amenable for dynamic programming, and its maximum number. So it's like the maximum independent set in a tree. It's a maximum independent set in a what is called an interval graph. Really, that's what it is. So far, so good. But suppose now here is an interesting observation which makes somehow life easier, is that there exists an optimum solution containing task 1, the one that finishes the earliest. Remember, I have arranged it in that has, or rather, the earliest finish time. I mean, it's the task or a task. If there are more than one tasks with the same finish time, you pick one arbitrarily. So, okay, this is I'll explain you what this observation means. This tells you that it is safe to pick the first task. that is so let's look at that example. We saw several optimum solution, right? The optimum number of tasks you can schedule in this example is 2. We said 1 comma 4 should so what is 1 comma 4 8 10 14 15 2 comma really 6 5 which is 6 10 10 16 and 1 comma 5 is 8 9 10 16. So there are 3 optimum solutions. So what I am saying is it is safe to pick one in the solution. Means what does that mean? It means that oh, there exists an optimum solution that contains task 1. Okay, I can prove. This is different from saying that every optimum solution contains task 1. That's really not true. Here is an example where here is an optimum solution that does not contain task 1. But I am saying what is task 1? The one which has the earliest finish time. The earliest finish time, go ahead and you can pick it into your solution. That is what this observation tells you. We will prove this observation, but let us understand what the consequence of the observation is. The consequence is that, remember, how did we do dynamic programming? We said we'll assume, so this is like an assumption. Some job k is in the solution, then you can break up my remaining problem into some recursive sub problems. But now here is saying you do not have to assume. I am telling you it is safe to assume that job 1 is in the solution. There exists an optimum solution that contains 1. So that means you do not have to try all possible choices of k, right? We did possible choices for k here. Try 1, 2, 3 up to n. You do not have to. 1 you can safely assume to be in the solution. That is what this observation tells you. So the consequence is that we do not need to try n choices. So the algorithm is pick one first task. This is the earliest finish time task, any one of them. Once I pick that, anything that overlaps with it, which means its start time is before this finish time, you cannot take. So throw them away. Now look at the remaining jobs and find the optimum. This is because of the optimum substructure property. So in terms of the recursive formulation, instead of there is a left and the right sub problems, we have only one sub problem. I pick one and then in the remaining find the optimum. Remaining that does not overlap with this, find the optimum. How do I find the optimum? I apply the same strategy, which is in this, pick the earliest finish time which does not overlap with this, add it, keep doing it. That is the algorithm. So the algorithm is pick one earliest finish time task. Throw away tasks that overlap with one. You can't pick it, so you can throw that away and repeat, right. So that means in the remaining tasks, pick the one which has the earliest finish time, throw away all the tasks that overlap with whatever you have picked, keep doing it. Finally, what you have is the optimum solution. And why is that? Because of this observation which I am going to give a proof of. Okay, plus the optimum substructure property. This observation says there is always an optimum solution that contains the earliest finish time. I take it, and then the optimum substructure property says that what is remaining is the optimum for the remaining things that don't overlap with this. Find the optimum. Well, okay, so that's optimum substructure. And how do I find it? There is always an optimum that contains the earliest finish time task in that remaining set. Pick that and keep doing it. So it saves a lot of time on from dynamic programming in trying to find various choices. Remember in optimum binary search tree or matrix multiplication, if we had such an observation that, oh, there is always this guy, there is always an optimum that contains this as a root, then I know I can just pick that as a root and then recurse, and in that I can apply the same algorithm, keep going. Since I did not have it, I was trying all possible choices for the root. But in this specific problem, I am going to prove that there is always an optimum solution that contains task 1. How do I prove this? The proof follows, again it is a standard template, okay. Suppose not, right. Let S be an optimum solution that does not contain 1. Which means I have a bunch of jobs. So, this is my earliest finish time, and then there are several other jobs. My S does not contain this. The optimum solution, an optimum solution. So, now what I am saying is, in the optimum solution, pick the one which is the earliest. Let X be the task in S with earliest finish time among jobs in S. Okay. Now, I remove X and add 1. I claim this is also feasible solution. This is also non-overlapping with whatever I have picked. Once I show that, I know that this is also optimal. Why? Because optimal is in terms of the number of jobs in your set. From your optimum set, I've removed 1 and added 1. So, the number of jobs remains the same. So, if I show that by doing this, removing the earliest finish time and adding my earliest overall finish time job, I have not disturbed the overlap property, which means that in this new set also every pair is mutually non-overlapping, then I am done. Well, obviously they will be, because whatever. So, this was the one, let us say, in my solution which had the earliest finish time, okay, that was not 1, and there are various other jobs. Now I have removed this and added another job which finished even earlier. So, clearly this new job which I have added will not overlap with anything else, because the task which I removed does not overlap with anything else, and I am adding a job which finished even before that. So, that means every other job started after that first task which I removed, and they will always also start with the task which I just added. So, they will not overlap, and every pair of them, they do not overlap anyway. They did not overlap before, so they are not going to overlap now. So, that is it. And so, let us call this S prime. So, cardinality of S is equal to S prime, and now S prime contains 1. So, what have I done? I have produced you another optimum solution that contains 1. You say, okay, here is an optimum that does not contain 1. I find the earliest finish time task in that set, remove it, add 1. that will still be mutually non-overlapping and the size is the same, and so I have proved what I wanted to show. I have provided you an optimum solution that contains task 1. Good. So, as a consequence we have, so this essentially is saying this is can be mentioned as a greedy choice. So, because of this greedy observation, we can save a factor of n in the algorithm. Okay, so that's what we have achieved from dynamic programming. So, if you what happens is, you have an optimization problem. Typically, try all possibilities takes exponential time. This is for matrix chain or optimum binary search tree. We said proportional to the Catalan number. Now, try all first or last choice, some choice plus optimum substructure property brought it down to typically some polynomial time. In fact, this may not happen in general. There are problems where even you can do dynamic programming also takes exponential time. That's for later. So, now what we are saying is greedy choice plus optimum substructure property saves a factor, because instead of, so even for that first choice or last choice, you are not trying all possible choices, you are making some greedy choice. Now, what is a greedy choice? There is no single definition for it. In this case of the scheduling problem, the greedy choice happens to be the job that finished the earliest, right? And that and it may not any greedy choice may not work, because we need to prove that there exists an optimum solution that contains your greedy choice, and we proved it, and that's how that greedy choice works, right? So, important thing in general, greedy algorithms do not necessarily give optimum solution. Okay, in the problem sheet I will give you a bunch of problems where I'll give you optimum binary search tree, matrix chain multiplication. These are also problems where you can think of some greedy strategy and try and argue that greedy actually does not give you optimum solution. Okay, how do you argue greedy does not give you optimum solution? You need to come up with some examples where greedy algorithm provides a certain solution, but the optimum is some other solution. Okay, I'll give you now. So, for example, let's come back to the same scheduling problem. As I said, what is greedy is not clear. It so happened that our greedy choice was the job that finished earliest. Somehow seems like a good idea, but then there are other greedy ideas you can think of for the scheduling problem, right? Imagine, just start fresh. You have to schedule a lecture room, and there are users are coming with the window of time where they need it. What job would you schedule it? What kind of heuristic strategy would you use? So, for example, for the scheduling problem, what about somehow job that starts first? Right? We said we will schedule a job that finishes first, somehow that relieves the resource for other jobs. But maybe I can say I don't want to keep the job lecture room unused for a long time because somebody is starting later, but I will pick a job that starts earliest, maybe schedule that job first. Does that give you optimum solution? No. You can come up with easy example. Okay. But let's say I have 1, 2, 3 tasks. This starts at 7 a.m. and goes on till 12 noon. This starts at 9, ends at 10. Another starts at 10 and ends at 11. So, you will schedule 7 and then you are stuck, because you cannot schedule 2 and 3. Schedule not schedule 7, job 1, because that's the earliest. I scheduled it, but then I'm stuck because that's taking 5 hours. You can't schedule anything else. Opt, in fact, is 2 and 3 because you can schedule both these tasks. Even though task 2 starts later, scheduling that seems like a better idea here. Okay, so here is an example where this greedy strategy of scheduling a job that starts earliest does not give you optimum. Okay. Okay, can you think of some other strategy? Well, you might say, well, in this example we are stuck because the first job takes the longest duration. So maybe schedule jobs that requires the least amount of time. Because again that releases my resources fast. Does that work? No. Again, you can come up with very simple example. 1, 2, 3. Let's say I have 4 and 8. Maybe 3, 9, 9, 14, and here is a job which starts at 8 and ends at 10. Okay. So the second job takes only 2 hours. The first job takes 6 hours, the third job takes 5 hours. So you will schedule this according to this heuristic, right? According to this heuristic, you're going to schedule this job. But then you're stuck. I cannot schedule first job because it is going from 3 to 9, it overlaps with 8 to 10. I cannot schedule third job because it's again going from 9 to 14. But opt is actually 1, 3. I could schedule 3, 9 and 9, 14. Then I could schedule 2 jobs. Okay. So again, here is another example where this particular greedy choice of scheduling the jobs that require the least amount of time does not work. Okay. So, 2 observations. First of all, what is a greedy choice is not always obvious and it may not be unique. There may be multiple greedy choices. Number 2, greedy choice may not necessarily give you optimum solution. in general. In fact, for most problems, they do not actually. So, in your curriculum, you may typically that do give optimum. Typically, I know your curriculum has this Huffman coding. Please again spend time describing the problem. Okay, each one is unfortunately in algorithms course, lot of new problems are introduced to illustrate something, but each problem itself is an interesting problem, has a history. So spend some time describing the problem before you throw the algorithmic technique on it. Huffman coding. Coin changing, this is another example where for certain kind of coins. So suppose I have like a denomination, coin denominations, $1, 50 cents, 50 paise, $2, $5, 10, 2 rupees, 5 rupees. Now I have to change 100 rupees with using minimum number of currencies or coins I want to use. So the greedy choice is that if you have, let's say, whatever the highest currency denomination you have, see, can you take the maximum out of it? If you want to change 100, let's say your currencies are 10, 5, 2, 1, then give as many as 10 rupees. Let's say I want to change 125. Give as many as 10 rupees, right? 12, 10 rupees will give me 120, and then I have 5. Okay, so this is a greedy choice. Greedily use as much of the highest possible currency, and then for the remaining use as much as of the highest possible currency and so on. This is a greedy choice, and that gives you an optimum solution for certain kind of coins. But if you change the coin denominations, they don't work sometimes. Okay. Minimum spanning tree, both algorithms you will see, the Prim's algorithm and Kruskal's algorithm, they all greedy algorithms give you optimum. Okay, but please you have to prove that greedy algorithm provides an optimum solution, because just describing the algorithm is not enough, because precisely the reason that greedy algorithms do not necessarily give you optimum solution. We have seen some examples for the same scheduling problem. I told you here are some couple of possible greedy choices that do not give a optimum solution. So for all the problems for which greedy gives you optimum, you need to prove something like this. There exists an optimum solution containing the greedy choice. So for example, for minimum spanning tree, if you apply Kruskal's algorithm, then you have to show that there exists a minimum spanning tree which contains the smallest edge, and if you have picked a bunch of edges and then you are picking the next smallest edge that does not form a cycle, that is what Kruskal's algorithm does, then there exists an optimum solution that contains all of this. So basically you have to say the first choice is correct, and if whatever you have picked is correct, then the next choice is correct. These two need to be proved formally for all the problems for which greedy algorithms work. Okay. Either you have to say first choice is correct and you have an optimum substructure property, then it's fine. Then what is the new problem? It's some sort of a recursive formulation, and you are applying greedy there. Or you have to say the first choice is correct, and if you have picked some k things, like by induction, you have to show that the next choice is correct. So you may not be doing the proofs. Teachers who are doing this, you may not be, I'm sure most of you do not give a proof of correctness. So but you need to give proof of correctness. So basically you have to say first choice is correct. What does that mean? There exists an optimum solution containing the first choice. So for something like Huffman coding, it's actually a complicated proof, because there is no such thing as first choice, second choice. You're just taking the two smallest frequencies and just sort of merging them. They become highest height. Okay, so please go look at the proofs. But and if my first k choices is correct, then the next choice is correct too. Okay, or you have to show optimum substructure property. Okay, you may not have time, or students may not have the ability to actually go through the entire proof. But for this scheduling, it was a very easy proof. We actually gave the complete proof that there exists an optimum, because it's in fact the entire most of the proofs are like this. This is what we call this cut and paste. Suppose not, then suppose it does not contain your first choice, then remove something. That something is important. It is carefully chosen, not always as easy as what we have done here. Remove something, put this, and you say that whatever is there is remaining feasible, and it gives you another optimum solution. So I provided you an optimum solution with my first choice. Okay, you need to argue this, and so all I'm saying is you have to at least tell the students that proof is required, and it can be proved. At least for one small example, give a proof. Minimum spanning tree can be proved. It's there in the books, again in Carmen's book. You can be proved. You should prove it. Students should realize that proof is required. Now you might ask, why am I emphasizing this proof of correctness for greedy, though we did not talk so much about proof of correctness of divide and conquer or dynamic programming algorithm? Good question. Merge sort, for example, we said we split it into two halves, sort each one and then merge. So this is not something that required a proof, because once you sort the first half, sort the second half, then the correctness of the merging algorithm gives you the correctness of this sorting algorithm. Okay. For optimum binary search tree or matrix chain multiplication, the optimum substructure property, along with the fact that we are trying all possible choices for the first or the last, gives you the correctness proof, because what we are trying, we are not omitting any solutions. We are trying every possible solution and picking the optimum, and instead of doing exponentially many choices, because of the optimum substructure property, we choose the optimum here, putting things together. So that equality, dynamic programming equality I write, usually the proof of that gives you the correctness of the proof of the algorithm. But for greedy algorithm, especially because it does not work most of the time, I have given you various examples in the problem sheet, you need to give proof of correctness, give at least one proof of correctness. Okay. The reason this is true is that later on, as I said, proof of correctness is important for every algorithm we do. Whatever we have done, we need to prove that correctness, whether it's sorting, searching, whatever, BFS, DFS, everything requires a proof of correctness, and they are largely implied, inherent, easy to show. And that's why later on we are going to come up with problems which are very hard. There is no easy algorithm. Greedy algorithms will be tempting, but you need to prove that they actually give you optimum, and almost often they do not give you optimum. Okay. So here I am just saying that greedy is a place where you need to get comfortable with proof of correctness, or to come up with examples where greedy does not work. Okay. So I have listed you some problems where greedy actually works, and maybe they are there in the syllabus, but just don't do only the algorithm. At least emphasize, even if you don't do the proofs, emphasize that the proof of correctness is required, because, and again give examples where greedy does not give you optimum. Okay. So that's all I want to say about greedy. So we have covered divide and conquer last week, and I think I've we have the good thing, I mean, dynamic programming is a little more robust because we're trying all possible choices, but greedy is faster because we save on certain choices, but we need to argue correctness when we talk about greedy algorithm. Okay, so that's all the algorithmic techniques, and once you do the problems, you will get even more feel for all these three techniques. So next week, I'm going to talk about basic graph algorithms, and then we move on to NP completeness.